So the binomial model assumes that continuously compounded returns are a random walk. In other words, it's not the prices that are a random walk, but it's the returns that are a random walk. And what we mean by continuously return is that just like continuous interest rates, the value of the stock price at time t plus h is the value of the stock at times t with an exponentiated continuous return. Now, this, if here R in this notation is a period return, it's more common to let R, let's call it R prime, to be the annual return. And then we would write this as ST e to the h R prime. In other words, it's usually more suggestive and more and I think clearer in notation to go by the convention that let's make our returns always be annualized returns, and then we will reflect the time period of the return through the multiplicative factor. And indeed, this is how we saw returns represented in our binomial lattice earlier, that the R and the delta and all those other symbols were annual numbers, and they were being multiplied by h to reduce them to the appropriate period. So what are some important properties of continuously compounded returns? Well, using logs, we can get the returns from the prices. Indeed, if we go back, so what does that mean? It means that the return is equal to HR, the period return. I'm going to use this notation because it's, I think, better. The period return, HR, is the natural log of ST plus H over ST. So if I have a price sequence, for example, if I had monthly stock prices, so H would be 1/12, then by taking the log ratios, the log of these ratios, I would get the 1/12 of the annualized continuous returns. So from prices, I can easily get returns. Similarly, from the exponential function, I can get prices from returns. And that was the original defining right here. We see that if I know today's price and I know the return, I know the next price. So they're quite easy to work with. Prices and returns can be very easily manipulated backwards and forwards. Then there are two other properties that are useful. One is continuous compounded returns are additive. This is a wonderful property. What does it mean? It means that if I have ST plus 2H, well, I know this is equal to ST plus H times E to the second period return. I'll call it HR2. But I also know that ST plus H is the ST times the first period return. In other words, the return for two periods is simply the sum, and here I'm working again with annual, that the return for two periods is simply the sum of the two annual returns. And the final thing is that even though the returns can be well under negative 100%, stock prices cannot go negative. And that's apparent from the model, that the stock price at time t plus h is equal to the stock price at time t times E to the HR. So even if we imagined an R of minus 1,000%, it doesn't matter what R is, that as a continuously compounded return, the stock price can never go negative because E to any exponent, no matter how negative, is always bigger than 0, and consequently, although the stock price will drop, dramatically, we cannot have a negative stock price. So this model has the essence of the random walk, but it eliminates all of the problems with the random walk discussed.